what is the most metal that we think of that you melt and form into a shape?
Yeah, so those are going to be polycrystalline. They're almost so, we're going to talk about ceramics as well. So those have many smaller crystals. So going back to maybe the silicon crystals that are in your solar panel, they're really pretty big. Just imagine now those centimeter sort of crystals that are bonded together are now on, say, the micron or nanoscale. So it's really ceramics are just crystals assembled that are on a small scale, and they're somewhat randomly oriented. They're kind of glued together haphazardly. And so then that's really a definition of a ceramic, which would be like an oxide like quartz. But metals have polycrystalline as well. So you have polycrystalline oxides, they're ceramics, and then you have polycrystalline metals. But they're both pretty similar in terms of having this type of structure. And the reason why oxides are so big is because we live in an oxygen environment, and not many metals survive our atmosphere. And so everything you dig up out of the earth is going to be a ceramic. So, and the ceramic tends to be an oxide. So that's why ceramics are such a big word, even though, there's they're polycrystalline and there's polycrystalline metals, but you don't call those, they don't have a special name. They're just still metals. Whereas, you go from a single crystal quartz to a polycrystalline quartz, and now you call it ceramic. I mean, there's no analogy for metals, but it's 3 millennia of people working with ceramics that's why it gets called ceramics.
Yeah, so talk a little bit about the manufacturing process of ceramics then. I guess if we don't call rock ceramics typically, it's normally referred to as some sort of manufacturing process that makes them a ceramic, right?
Absolutely, yeah, that's right. So traditionally, I mean, ceramics, everyone knows, have been around for a very long time. So there's some real basic ways to make ceramics. You think about clay pots and that sort of thing. You just mix some water with like a powdery substance, and the water acts as a natural glue for clays. For some of the more technical ceramics, you have to add your own glue. So not every ceramic is as nice as clay in terms of forming. So clay is pretty amazing. When you start adding water, you form this mix that has its own sort of plasticity. In itself, clay is a pretty amazing material. The technical ceramics are made a little differently. Like if you think about electronic components, there's a lot of electronic components made of ceramics. There's substrates that you use to populate like high temperature chips and stuff like that. And these tend to be like aluminum oxide. And there they tend to use something called tape casting. And tape casting is where you take a slurry, and a slurry is just a mixture of a liquid with the powder in there. And then you pour the slurry on glass, and then you smear it out with something called a doctor blade. And the doctor blade's set at a height, maybe sometimes it's tens of microns, so pretty thin. And that slurry then dries, the solvent comes off, leaving the ceramic particles on the plate. But then there's also a little bit of glue, like a plastic that keeps all the particles together. And so you then can peel it off, and then you can start laminating. You could start printing on that, almost like paper. It's a lot like paper. And so that's the way circuits are made. So when you go from, say, you want to take the signals out of a chip and go to another chip, you could either use that green board you see on your computers, with its traces, or you could use these really little ceramic chips to bond the silicon chips on. And those are very fast and very efficient. So that's another ceramic process called tape casting. So yeah, a lot of ceramic processing is very traditional, but then there's new ones that are pretty interesting for making technological components, which is pretty important. For example, multi-layer ceramic capacitors. There were well over 1 trillion made last year, so it's a huge business. There's hundreds of these multi-layer ceramic capacitors in your cell phone, hundreds in your computer. So it's sort of a big business, and companies have really gotten good at ceramic processing to make these sorts of chip capacitors out of ceramic.
They basically come from clay or some small particles that you just stick together, right? When I was learning this, I thought of it as like packing a snowball, basically, right? You have a bunch of little snowflakes, you stick them together, and as you press harder and harder, and it warms up a little bit, particles start to stick together then, right?
but then you have to heat it. So that's only the first part. And I guess that's one thing I didn't talk about. So that brings up something called sintering. So that's what the kiln is for. So now do you form this great, nice shape? You've made your pot and you want to, you want to fire it, right? So what does that do? So you mentioned the snowball where you're basically packing. Well, when you pack something, it may be like 50% solid, but there's a lot of air, maybe 50% air. And so how do you get rid of that? You can only press on things so much to get that air out, and you still have maybe 20, 30% by volume air, maybe more. How do you get rid of that? Well, you heat it up to really high temperatures, glowing red hot. And then once you do that, then actually the atoms of each particle start moving to minimize the surface. And then they basically kind of glue the particles together. There's people who study sintering for a living, but basically it's just minimizing the amount of porosity within the ceramic. So you go to high temperature, some ceramics sinter at 1500 centigrade, so 3000 Fahrenheit and above. So you have to go really hot. Some of the really technical ceramics, you have to go very high in temperature. So that's another definition of a ceramic, something you have to process like that.
We talked about some applications of ceramics. You talked about all the different manufacturing processes and how they're pretty specialized for the application, especially in terms of, I guess, the geometry of what you're trying to get to. You'll see the ball bearings now are often being substituted. You even see ceramic knives and things like that. Yeah. So do you want to talk about why that is? Like, I suppose they're hard, but
that's why
they're often, yeah. But I suppose the normal problem is just that they're brittle, right? That seems to be always the trade-off with all these sort of materials, is the brittleness versus the hardness. If you want to just maybe talk a little bit more about how that works and how we engineer those different materials.
Yeah. So when we talk about ceramics failing, they always tend to fail in tension. So what that means, if you have a crack that's starting to open at the very tip of the crack, ceramics don't blunt most of the stresses at the crack tip. And so what happens is in metals, the metal around that crack tip will flow a little bit and deform to basically blunt the stress at that crack tip. So if you can figure out ways and applications where mostly the application for the ceramic, if it's in compression, you don't really worry about opening up that crack. It's basically you're always compressing, right? So that when you think about a ball bearing, you think about mostly compression, right? Running in a raceway and supporting something. And you mostly think about that application, that ball bearing being in compression. And so that's sort of an ideal scenario for ceramics, is they don't really fail as much in compression as they do in tension. The other thing that's really nice about ball bearings, especially, is the wear, right? So ceramics just don't wear out. They don't wear out like metals. And we think about ceramic knives, you can hold the edge, right? So you can hold the edge much better in a ceramic knife than a metal, where it sort of blunts and sort of basically over time will wear down. So in any wear application involving compression, ceramics are really, really good at that.
Mm-hmm. So yeah, when we think of hardness, normally think of like their ability to scratch each other or something, but there's also metal ball bearings get kind of squished, you can see sometimes, right? Are those different properties that relate to being squished versus being like scratched, or are they the same thing?
Well, scratching, but basically the plasticity part of squishing versus the plasticity part of blunting that crack, that is the same thing. So for metals, that's why metals work so well, because they're able to plastically deform under stress. So you could even think about plastic deforming, about squishing the ball bearing, or just like blunting a crack. That both is the same reason for metals anyway. I wanted to go back to hardness though. So of course the hardest material is diamond, and so that sets the bar for the scale. And then the next ones are ceramics. So like zirconium oxide, you can actually fake diamonds or zirconium oxide, but you can also make a ceramic out of it. And that is a classic ceramic that has really a lot of hardness to it. And of course, silicon nitride and silicon carbide, these are really hard ceramic materials. So that's one reason why ceramics are used in all these, like, cutting bits and stuff like that, tool bits, stuff like that.
So the hardness also probably matters a lot. I know they make bulletproof vests now out of ceramic plates and not metal plates. So the hardness there, I guess, matters more in some sense than the brittleness when you're
Right.
comparing
That's right.
metals.
Because the metal, because it deforms, it may not stop a projectile, right? I mean, you think about a projectile coming in and then the metal plastically deforms. Well, it can't plastically form too much because then it'll allow the projectile to pass through. I'm not an expert in this area, but I can see that being one of the reasons why metals. Also, it's just the density of these. Like metals are like 5 times more dense than ceramic. So just the weight factor probably also affects, like I said, I'm not an expert, there's a lot of armor experts, but these are like silicon carbides, probably silicon nitride, I'm guessing, where they make these plates and they just, put it in a vest and they're not shaped. I don't think they're shape form. I know they're trying to, but a lot of them are just pockets you put them in, and once they are used and saved your life, I guess they just kind of put a new one in and that's it. So yeah, I think the hardness helps a lot and prevents a lot of penetration that way. And the strength to weight ratio is really high.
Mm.
So I think those are all really important for designing armor for sure. Ceramics are pretty light in comparison to metals.
Okay. A few more applications I want to go through just that I think are cool for ceramics. Space shuttle tiles, of course, are
Yeah,
famously.
I was gonna mention that one. That's how I got into materials in the first place. So the space shuttle has on the outside of it a thermal heat shield made of, I think it's mostly silica, where it's a very, very porous material that doesn't allow much heat to be transferred. It's pretty amazing. So they put these shuttle tiles, on the outside, and once it goes through the atmosphere, it heats up, but basically keeps everything pretty cool on the other side. But the temperatures that they get to, you need something like a ceramic because not only does it have to have good thermal properties, low thermal conductivity, but it also has to be able to handle that heat. So it tends to be really porous, really small, fine particles that are glued together, but with a lot of air in between. And mechanical properties are tough because you can imagine something like a sponge made of these particles, and the mechanical properties are really hard to. So it's hard to optimize the mechanical properties and the thermal properties. So the engineers who designed these thermal spatial titles had to really consider both of them and sort of maximize both. And of course, we know that there still was some problems on them adhering and staying on, and that's the mechanical part, right? So you're trying to average the or optimize, I should say, the mechanical and thermal, but certainly a really cool application.
And relatively light, I would assume, like you said, because
Yep.
that's really important for
Aerospace.
yeah.
Absolutely. Yeah.
Okay. Okay, good. And spark plugs are also.
So they're really good insulators. And so, an insulator is, for example, something like your plug in the wall is polymer, mostly is plastic, and you have two wires coming out of your wall and they're surrounded by this plastic. Well, that's just fine. You can offset that voltage, normally 100 volt or so. The spark plugs tend to be at very high voltages, not much in terms of current, but a lot of voltage. And they have to run at high temperature, right? So now you got this really tough environment. It's basically at the top of the piston. And so you got a really rough environment, a lot of heat, a lot of vibration. And so ceramics are really the only material that can be an insulator, which means not conduct electricity and handle the heat. And so that's a really interesting application. And one of the biggest things they have to do is they have to make the ceramic thick enough to support the voltages, which are, I don't know, kilovolts or something like that. So, you have to worry about the dielectric breakdown. It's almost like the mechanical breakdown, but in this case, it's enough of a voltage that will fail the material. So ceramics are really good at holding high voltage. For example, if you go just look at utility poles outside, you'll see like on the really high voltage wires, you'll see these sort of things that are connecting them, and those are ceramic. And you'll see sort of these things, they almost look like upside down dishes. And those are basically isolating the different wires, and that's a ceramic as well, or glass. Sometimes they use glass. And so for any of these electrical insulation applications, ceramics and glass are really, really useful.
Mhm. So I always wondered, so they're good, both electric and thermal insulators. Is there a relationship between those two? I always wondered
Yeah,
if there's.
absolutely. So like metals, a lot of the thermal conduction in metals is just electrons being transferred. So it has to do with electrons carrying the energy from one side to the other. So yeah, if you have an electrical insulator, that means the electrons aren't really traveling. And so they're not carrying electricity, nor are they carrying heat. They're basically eliminated the one mechanism of transferring heat in a material. It's electronic. Yeah.
Okay.
So metals are sort of really good thermal conductors normally. So they
Uh-huh.
do go. And that's one of the biggest problems trying to find a material that's a good electrical conductor, but a poor thermal conductor. There are applications for that, and people are working like crazy to find that. And for energy applications, if someone found that, that'd be big. That'd be huge.